Section 14.9 in the Klein's textbook takes you through the sharpless asymmetric epoxidation. Now, this is a modern technique that uses chiral catalyst to control the stereochemistry of the epoxide that's formed. Now, if you have an alkene which is flat, epoxidation can happen from the top face or the bottom face with an equal 50-50 chance, just like flipping a coin has a 50-50 chance of heads or tails. Now, if you use a chiral catalyst, this system allows the reaction to only occur from one face of the molecule with very good predictability, yields, and enantiomeric excess. If you look at this chemical reaction here, you can see that it has very strange reagents. You've got this tert-butyl peroxide, but that is just like a peroxy acid. That's your source of oxygen, and I'll indicate that as an oxidant. You've got this titanium tetraisoperoxide thing in there. The purpose of that is a Lewis acid that brings together the chiral catalyst and the allylic alcohol so that it will deliver the oxidant from preferentially one side. DET stands for diethyl tartrate, and that's actually the chiral additive that's used to control the stereochemistry of the outcome. So if you look at this molecule here, the only way the sharpless asymmetric epoxidation can work is if you have this handle here, okay? That's an oxygen atom with some lone pairs that can coordinate to the titanium atom and allow the whole trigger of events to happen so that epoxidation happens in only one fashion or another, okay? If you use one enantiomer of diethyl tartrate, you'll get one molecule. If you use the opposite enantiomer of diethyl tartrate, you'll get the enantiomer. So it's a really cool reaction, and you don't get a 50-50 mixture. You get very good, almost pure one isomer that you want, okay? So that's the sharpless asymmetric epoxidation. It uses chiral catalysts. Now, if you did this reaction with MCPBA, you would get a perfect 50-50 mixture of this molecule on top and the molecule on the bottom. This would not do you very much good if this molecule was only biologically active in one stereochemical form, or if you needed one stereochemical form to synthesize a more complex natural product with a certain type of configuration of stereogenic centers, okay? Now, how do you predict which product you're going to form? A tool is shown here. It's kind of a mnemonic or a tool here. What you do is you position your allylic alcohol in the plane with the OH group pointing towards the northeast corner, okay? And then if you react it with the plus diethyl tartrate, it's going to come from the top, so just think plus from the top. And then if you treat it with minus diethyl tartrate, the epoxidation will happen from the bottom face, okay? So let's see how to use these tools. This is problem 1416 in the Klein's textbook, and you've got this allylic alcohol here, okay? We call it allylic because the alcohol is one carbon away from the alkene, okay? Now, if you try to rotate that around, you could move your computer or you could twist your head like this if you wanted to. You'll see the oxygen will be in the northwest. You want this to be in the northeast. So the way that you have to position this alcohol in the northeast is to take your molecule and flip it upside down, okay? Now look at the reagents that you're using. You're using the plus diethyl tartrate. So remember, the plus diethyl tartrate is going to give you the epoxide coming up right from the top face of the molecule, but we had to flip that molecule, okay? So if you take this molecule and you flip it upside down, well, if you flip the OH up there, so it looks like more orientated exactly like the the molecule here in the figure. Maybe I shouldn't draw too much on this. And then, so the plus diethyl tartrate is going to react from the top face. So that's going to form the epoxide. And we want to use wedges to show how it's going to be on the top face. Okay. And then this carbon here, this group here, we need to draw going behind. Okay. We can't have two wedges on the same carbon. So that's going to be going back. Okay. Going back. So that's what happens to the allylic alcohol part. Okay. Let's do another problem to see how this works. In this molecule right here, okay, this is the one you definitely need to flip upside down. You can see how this oxygen is going to the southeast. We want this to be on the northeast. So you're going to take this molecule and flip it upside down. Okay, we'll do that here. Okay. So that's the same molecule. Remember, alkenes are flat, so I've basically taken that molecule and flipped it over like that. And now we want to think about the reaction conditions. Here we're using the minus diethyl tartrate, and just remember minus is below, and so that's going to be from the bottom face of this flat alkene. So that's going to give us an epoxide where we want to draw the epoxy group with two dashes, okay? And this allylic alcohol portion with the carbon and the OH is going to be coming up, okay? Up. Whoops, forgot the carbon. Okay, so that's a little bit about the sharpless asymmetric epoxidation. If you do want to do this reaction and you're taking my course, we just simply draw it like this, SAE, okay? Now, underneath this, you do need to say plus or minus diethyl tartrate, okay? So SAE means sharpless asymmetric epoxidation. I figure if you needed to do this in your basement, say, you would, Google and find out, the different reagents, okay? So what molecule is this going to make, right? So you need to flip this around, think about the mnemonic, and then this is going to be coming from the top face. So this is going to give you that molecule there. And I think that's right. I don't know. I get a little confused myself looking at these things. Okay, so anyway, SAE is what I wanted to focus on. That stands for sharpless asymmetric epoxidation. Okay, so thanks for watching. I hope this kind of gets you started on thinking about the sharpless asymmetric routes towards epoxidation.